This episode of 365 Days of Astronomy is sponsored by no one. This show relies on the generous contributions of listeners like you. For just $30 a day, you can help us share astronomy with the world. Please consider donating at 365daysofastronomy.org.
You are about to listen to the 365 Days of Astronomy podcast.
What do they talk about?
Astronomy, stuff that's far away.
How far?
How far? Well,
This stuff is far. It's really far.
This stuff is far, far, far away, and we're talking far.
Like uber far.
You can't get there by car today. It's super duper crazy far, but not just pulsars, quasars, and stars. We mean it's far,
Far, far.
If there's some doubt, listen to a shout.
This stuff is far.
the IYA 365 Days of Astronomy podcast starts now.
Hi, this is Steve Nerlich from Cheap Astronomy.
www.cheapastro.com.
And this is Greenhouse Earth, the Restless Planet. This is the second of two podcasts on what astronomy can tell you about climate change and global warming. Last episode we dealt with fairly modern Earth history, looking at the causes of glaciation cycles in the last 800,000 years, which are sometimes mistakenly called ice ages, but really ice ages are measured in millions of years, and we are in one now. It's called the Quaternary Ice Age, since it's in the current Quaternary geological period. Possibly the first ice age ever, the Huronian, is more hypothetical than evidence-based and is somewhat speculatively positioned around 2.7 to 2.3 billion years ago, and was probably caused by biology and a slightly cooler sun. When life, at least archaean and bacterial life, first took hold about 3.5 billion years ago, it's speculated that the sun was around 10% cooler than it is today. However, Earth's atmosphere was very rich in carbon dioxide at the time, so as cyanobacteria began to actively photosynthesize, they began to change the atmosphere by adding oxygen and extracting carbon dioxide, which after 800 million years or so resulted in an atmosphere a bit more like the one we have today. So a combination of low atmospheric CO2 and a slightly cooler sun may have brought about an ice age lasting hundreds of millions of years. Apart from the Huronian, ice ages and the lack thereof, being those long periods of global warming that don't really get a name, all seem to be largely the result of continental drift and its impact on ocean currents. If we divide the Earth's surface into land, water and ice, we find ice has the highest albedo, reflecting back most of the sun's radiation, while land is more likely to absorb some heat, but still reflect a bit back, and then water, having both a lower albedo and being a rapidly convective fluid, not only absorbs more heat, but is also an excellent heat buffer, absorbing heat during the day and then releasing it at night. This is why you experience generally warmer nights on the coast than you would do further inland. So, across the history of continental drift, it tends to be the case that if you have a lot of tropical oceans, Earth's mean global temperature is going to be warmer than if you have a lot of tropical continents. However, a bit of an exception to this rule is now, where we do have a fair share of tropical oceans, but we are still technically in an ice age. After all, over 10% of the Earth's surface is currently covered in permanent ice. This is thought to be because the present configuration of continents limits the circulation of warm water from the equator out to the poles. If you look at a world map, the Arctic Ocean is semi-landlocked by Siberia, Alaska, Canada and Greenland, and at the South Pole, the large majority of the southern ice cap is on land. Of course, in earlier periods of Earth's history, everything was different. There is thought to have been a cyclic pattern to continental drift, where you start with a single supercontinent, which fragments and various continents spread out, but later on they tend to recongregate to form another supercontinent. So what's really just the last of many supercontinents, Pangaea, formed around 300 million years ago from a previous generation of continents which came together from the fragmented Pannotia supercontinent, formed about 600 million years ago, and before that was Rodinia, about 1 billion years ago. Then, getting a little speculative here, there was Columbia sometime before 1.5 billion years ago, Kenor Land more than 2 billion years ago, at 3 billion, and Valbara at around 3.6 billion. After which we start getting back towards the period of heavy asteroid bombardment, and everything starts getting a bit molten-y. Across these sort of timescales, climate is largely influenced by what kind of surface the sun is shining on and whether there is significant flow of ocean from the equator to the poles. Greenhouse gas formation from volcanic sources may also be significant, as it's speculated that there is more volcanic outgassing when the continents are being actively spread apart than when they're all bunched together into one supercontinent. The most severe known ice ages occurred in the aptly named Cryogenian period, which persisted for about 100 million years between the time the supercontinent Rodinia began to break up and transition towards the Pannotia supercontinent. At that time, life was still limited to the oceans, with sponges being about the most complex life form found in the fossil record. Ice ages in the Cryogenian period are hypothesised to have been severe enough to produce a snowball Earth, where pretty much all land surface area was covered in ice and sea ice extended down to the equator. Some evidence for this comes from signs of glacial erosion from rocks considered to have been tropical at that time. Computer modelling suggests that a critical point is reached if ice gets to within 30 degrees of the equator, at which point a snowball Earth with total ice coverage is inevitable, as the high albedo of the ice reflects solar radiation back into space. Such an extreme might be achieved through continental drift of heavily glaciated continents to lower latitudes. Well, maybe. A reason to doubt the snowball Earth hypothesis is that CO2 levels in these early eras of Earth were still significantly higher than they are today. It wasn't until trees and forests really took off in the Jurassic period that CO2 levels started to decline towards today's levels. Indeed, during the Jurassic and Cretaceous periods, oxygen levels were higher than today, perhaps due to the explosive growth of trees and forests, which only became limited by the later evolution of species that could effectively live off them and limit their growth. But hopefully our predilection for cutting down rainforests will have no effect whatsoever. Something else we haven't really covered is the presumably major influence of ocean currents on ancient climates, but unfortunately the geological record doesn't have much to say on ancient ocean currents. It is, however, possible to predict their future movement from today. Climate change deniers point to the risk of a pending new glaciation cycle as a rationale for embracing anthropogenic greenhouse gas production as a good thing, since we are otherwise going to experience loss of habitable land area and reduced crop production as the Earth ices over again. However, there's another theory that states that if you melt all the Arctic ice in a carbon-driven global warming scenario, it will dilute the far northern seas, stopping the normal downward movement of dense cooled water, and hence stopping the stream of warm water, which is normally drawn up from the equator to replace the cool water, and snap, instant ice age. Well, after all, the ice has melted once and flooded lots of coastal real estate. So look, maybe everyone can come to Australia, or just make a choice to embrace modern technologies and replace cheap, but in all other respects dirty and inefficient, technologies. It's time to move on. Let's fix this now and then start work on the asteroid defence system. Then it's time to start thinking about the biggest climate change of all, when the sun becomes hot enough to evaporate all the oceans in about 1 billion years or so. If we can't save the planet, or at least its inhabitants, time is running low for something else to evolve that can. Thanks for listening. This is Steve Nerlich from Cheap Astronomy, www.cheapastro.com. Cheap Astronomy offers an educational website where thinking globally can save you the Earth. No ads, no profit, just good science. Bye.
You are listening to the IYA 365 Days of Astronomy podcast. Cool.
The 365 Days of Astronomy podcast is produced by Astrosphere New Media Association. Audio post-production by Preston Gibson. Bandwidth donated by Libsyn.com and Wizard Media. Web design by Clockwork Active Media Systems. You may reproduce and distribute this audio for non-commercial purposes. Please consider supporting the podcast with a few dollars or euros. Visit us on the web at 365daysofastronomy.org or email us at info@365daysofastronomy.org. Until tomorrow, goodbye.